Hello everyone, welcome back to my channel. My name is TJ Astrophysics. I'm a student at LLFP and today we're going to be talking about time, the fourth dimension. Come on man, it can't be that hard. Just got the hands ticking on a clock indicating that a second passed. You've got 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. That's all you need to understand time. There's nothing more to it. Well, yeah, but it's not that easy. In fact, it's a lot more complicated. That's why today we're going to have a deeper look on time and we're going to try to figure out exactly what it is. No one really thinks about it because we're not free to move forwards and backwards in time. Or are we? Now, time is very different than the three space dimensions that we experience: up, down, left, right, forwards, backwards. The difference is that we're free to move in the three space dimensions, but we're not that free to move in the time dimension. Yet space and time are part of the same continuum. Space and time are connected because they affect one another. But how do they affect one another? For us to understand that, we're going to be doing a little thought experiment. This is the same thought experiment that led Einstein to his first theory of relativity in 1905. So let's imagine that we're reading the time on a clock. Now we can read the time because there's light coming from a light source, bouncing off the hands of the clock and coming to our eyes. We know that light travels at a constant speed of about 300,000 kilometers per second. But what if, before the light reaches to you, you move away from the clock at the same speed, 300,000 kilometers per second? Then, for you, time would freeze. Literally. What? That is so cool! So time can literally freeze? How cool would that be? But I don't get it. How does it work? You still don't get it? That's fine. To make this clearer, we're going to be using something called a photon clock. So we're going to be imagining two parallel mirrors. And we're going to have a photon bouncing between these two mirrors at a constant speed of about 300,000 kilometers per second, which is the speed of light. And a photon is the particle of light. So we have our photon and it's bouncing up and down between the mirrors. If we follow the trajectory, it's going to have the trajectory of a straight line right here, and it's going to be going up and down in that line. So our photon is bouncing up and down at 300,000 kilometers per second, but the whole system isn't moving. So here the system didn't have any velocity. What we did up here is that we took the whole system and gave it some velocity. We took different pictures of the system at different times, T1, T2, T3, and so on. Now, if we look at the trajectory of the photon, it's different than this. The photon follows a sort of triangular trajectory, unlike here, where it just follows a straight line. But what does that mean? So here, without the system having any velocity, at T1, the photon is going to be here. At T2, the photon is going to be up here. At T3, it's going to go back down here. At T4, it's going to be here. At T5, up here. And T6, back to the top. Now, this is where it gets really interesting. In this case, between T1 and T2, the photon traveled this distance. But in this case, between T1 and T2, the photon traveled this whole distance. How can that be if the speed remains constant? So, in the same amount of time, which is between T1 and T2, in the first case, the photon traveled a smaller distance than in the second case. How can that be? Traveling a bigger distance in the same amount of time. There are two possibilities. Either the speed of the photon increased for it to travel a bigger distance in the same amount of time as a smaller distance, or time slowed down. The first option seems more reasonable, but we know that the speed of light remains constant at a speed of 300,000 kilometers per second. That leaves us with the one and only possibility that time slowed down. That is to say that the faster you move through space, the slower you move through time. Now let's take that and apply it to real life. If you had a twin and you were to take a spaceship and go 99% the speed of light for 1 year and come back, you would have aged 1 year, but your sibling would have aged a whole 7 years. And yes, that applies to biological effects too. He would have grown a lot faster than you, and you would have grown a lot slower than him. This concept is known as time dilation, and it's one of the coolest things in the world. It actually has an equation, which is on the screen right now, and it's fairly simple, where t prime is the dilated time, t is the stationary time, v is the velocity, and c is the speed of light. There's even an online calculator for time dilation, whose link is on the top right corner of the screen right now. It measures the dilated time depending on the speed you're going at and the elapsed time of the body at that speed. But your speed isn't the only thing that affects the flow of time. Gravity does too. In my video on gravity, I mentioned that gravity is the consequence of warps in the fabric of space-time. Space-time, because space and time are part of the same continuum. Now, it's really easy to visualize how gravity affects space. I did that on my video on gravity, and if you want to visualize it, go and check that out. But it's not as easy to visualize how gravity affects time. Now, it's not easy to visualize because time isn't a physical thing. But the concept is pretty simple. The stronger the gravitational pull, the slower time proceeds. So, time proceeds differently on Earth than it does at the surface of a black hole, because a black hole has a much stronger gravitational pull, so time proceeds slower there than it does on Earth. This even applies to smaller scales. Time ticks slower at the center of the Earth than at the surface. If I were on the surface of the Earth and you were up on a mountain, to me, your clock would be ticking faster. But to you, my clock would be ticking slower. There's nothing wrong with our clocks, it's just that the gravitational pull at the mountain and at the surface is different, and that affects the flow of time. All of this is to say that time is relative. Each person carries their own clock and experiences their own flow of time. And yes, your head is ever so slightly younger than your feet. Thank you all for watching. I really hope you're enjoying this content. If you are, please like and subscribe, as it means a lot to me. If you have any other suggestions for future videos or any questions, leave them in the comments below. Bye bye.